electronegativity. Now, in short, what electronegativity means, it's the ability of atoms to attract shared electrons. I'm going to put in brackets here because it's quite important. Noble gases don't have one. Now, there is an exception. Of course, chemistry is full of exceptions. Krypton has one. However, it is out of the scope. It is quite advanced, so we're not going to be touching upon that one. Now, let's have a look at two examples here. Let's have bromine. It's going to have a -1 charge because as an ion, it's going to take an electron to become stable. And then you have potassium. It's going to lose an electron to become stable. Now, we're going to have bromine here. Let's have potassium here. Now, we have to look at it again. Should know why it's larger. If not, please look at the video regarding the atomic radii and the ionic radii as to why this is larger. So, bromine. Let's have positive in the middle in our nucleus. Let's have the same thing for potassium. However, this potassium is going to give an electron to the bromine. So let's have the electron here. I'm just going to shade it in white here. That's the electron. It's spending more time with the bromine. The reason why is because bromine is more electronegative. So if I were to draw a dipole, this is what it would look like. The arrow will be pointing towards the bromine because it's more electronegative in that area. Whereas for the potassium, this little crest over here, a little bit of a T, kind of like the cat ion. It is a cat ion, okay? Think of that as a resemblance over here. Now, bromine, more electronegative, so it will spend more time with the bromine. Now let's have a look at, let's have our chlorine. Again, this is an L, so ClCl. Let's have our two atoms. Let's pretend that they're the same size. Okay, assume they're up to scale, same size. And then let's have our negatives here. And as you can see, they are equally shared between the two. This electron that is being given off going towards there. This electron as well attracted towards there. This one attracted towards here. This one attracted towards here. Obviously because positives and negatives want to attract. There is no real dipole. This will be no net dipole. There is none because as you can see, they are shared equally between the two. Now, we're going to have a look at a couple of examples. Let's have a look at, let's say, PO43 minus. Now, if you look at the electronegativity chart, right over here on our periodic table, you see the electronegativities on the top right corner. All right, as indicated here. So let's have a look at which one in our PO43 minus in our drawing is going to be the central atom. Look at phosphorus. It has 2.19. Oxygen has 3.44. Obviously, which one has a lower electronegativity? The lower electronegativity is the phosphorus. So, if we were to draw this out, our phosphorus would be the central atom. And our oxygens would be around it. All right, and then they would be drawn in this fashion. And then this would have 6 valence electrons, because we all know oxygen has 6 valence electrons. Yeah, so, and then we can have some double bonds as well. Well, we have a double bond here, a double bond here, and we can have a double bond here. Now, 1, 2, 3, 4, 5, 6, 7. Unfortunately, phosphorus can only have a valence of 5. So this would not be possible. So we would have to change this up and make sure that phosphorus has 5 valence electrons. If we do it this way, as we can see, 1, 2, 3, 4, 5. So this has 5 valence electrons. This is how it will look like. Now, the other 3 negative charges would have to be here, here, and then here, because then an extra electron got added. Now, this isn't necessarily the full version of how to do this. That's for another video. I just want to show you an interpretation of what would be the central atom in a Lewis structural diagram like this. We can do something similar. Let's actually do sulfuric acid. If we have our electronegativity chart, we look at our sulfurs, 2.58. You look at your oxygen, 3.44, and you look at hydrogen, it's 2.18. The lowest electronegativity is hydrogen, but this would be an exception. This would not be what we use as a central atom, not central. Now, simply put, it's because hydrogen can only have a maximum of 2 valence electrons, so it just would not make sense to put it as a central atom. Again, in another video, we'll look more at the Lewis structural diagrams, and it will make a lot more sense where I go into detail, and I'll be using about 10, 15 examples with you. For now, I just want you to understand the concept of the central atom. It is the least electronegative. However, hydrogen is an exception. It will never be the central one. So, between these two, it would be the sulfur. So, sulfur would be in the middle. We would have our oxygens kind of surrounded. And we know that sulfur needs to have a maximum of 6 valence electrons. So, again, this is 1, this is 2, this is 3, this is 4. So, some double bonds can form. Double bond has formed. Double bond has formed. 5, 6. So we're still safe with 6 valence electrons. So then where would be the other hydrogens? Would kind of be here on the sides. And then that way, this can also be stable, the 2 oxygens. Again, I'm just trying to reiterate the central atom here. We will go more deep into the details for the Lewis structural diagrams a little bit later as to how I know why the hydrogens are here on the outskirts and why the oxygens here are going to be double bonded, and whereas these ones are not, in regards to the greater common multiple of 8 rule. And again, we're not completely finished. We haven't drawn our valence electrons here either, but again, that's not the point of the lesson today. Now let's have a look at a couple more examples. Let's cover this one. Using diagrams, show how electronegativity and electron affinity are different. Well, the biggest difference between the two is, well, electronegativity, like we said, it specifically has to do with the ability of atoms to attract shared electrons. Electron affinity is not. So if I were to do it best, let me show you using a diagram for electronegativity. Let's say we have 2 different sized atomic radii of atoms. Positive charged, positive charged. The electrons that are on the outskirts here have a attraction towards this positive. So does this one, this positive, and this positive. How much of this positively charged nucleus is going to be attracting these electrons here towards it, like I just showed you with the arrows? How much of a strength of a pull does it have on these electrons? That's pretty much electronegativity. Guess what? There's maybe electrons here as well. These electrons want to attract towards this positively charged nuclei as well. it's going to have this, our positively charged nuclei, is going to have a pull towards these, from these electrons toward it. So it's the ability of this atom here to attract the shared electrons that are within the barrier between the two. Just like how this nuclei, the protons here, want to attract these shared electrons that are in the middle of the barrier as well, towards it as well. Now, where can it get a little bit tricky? When you have two atomic radii that are the same in terms of the picometer length, this can be a little bit more tricky because you have negatives that are shared between them equally. Now let's look at the electron affinity. Electron affinity, as we looked in the previous video, electron affinity has to do with the ability of this electron of wanting to be added onto this element here, right? This here would be beryllium. So this electron can either be added onto a 2p orbital, or it can be disregarded. Energy gets added onto this beryllium because beryllium is absolutely not going to be giving off energy. It's not going to lose energy. It'll take the energy and it would get rid of this electron here. So we'd get rid of that. In short, what are we trying to distinguish? The electron affinity is about the receiving of electron and how much energy is going to be released or absorbed for that electron to be gained. And in some cases, like I said, as an exception, it might get rid of its electron here so that it does not have to open up another subshell. Electronegativity has nothing to do with that. It's not about the amount of energy released or absorbed to get the electron. It's about the sharing. It's the ability of this atom here in hindsight of trying to take these electrons, because remember, only the electrons move. Or in hindsight, this atom here taking these electrons and sharing those towards it. Now, just letting you know, it's not just that these electrons want to go over there. Remember, these electrons also have some sort of attraction of effective nuclear charge with the nucleus here. And these also have the same with its own nuclei. But also as well, this electron and this electron do not like each other, so there will be some repulsion. This one and this one do not like each other as well. So there is repulsion between here as well. All right. Now let's have a look at another example. Explain the relationship between electronegativity and the size of an atom. So let's have a look at, let's say, cesium here. And let's have a look at, let's say, silicon. Silicon is a lot smaller. Again, if you look on the periodic table, based on the trend, remember, it increases this way. Increase in atomic radii. So cesium is obviously down here. Silicon, closer up there, so it's going to be smaller. Now, the electronegativity difference between the two. We have positive here for the silicon. There is electronegativity for these electrons, and these electrons here on this silicon and these electrons on this cesium, as you can see, they are extremely close together. The electrons here, very, very, very close to the silicon. This means that the silicon is able to attract these electrons quite well toward its center. However, let's look at another example here to contrast that, where let's say we have silicon, and then we also have, let's say, fluorine. Silicon, let's say it's that same size. Okay, I know it looks a little bit bigger here, but imagine they're the same. And let's say we have fluorine, which is extremely small. That small. As you can see, big difference. This fluorine is extremely small. It's on the very top right of our periodic table, somewhere around there. Its ability to attract these electrons that are shared between the two. Remember, there is sharing between the two. Look how close it is toward its nuclei. It's a lot closer than the distance between this to this, the cesium's electron with the silicon's center. This is why fluorine has such a great ability to attract these electrons that are being shared between the two to the middle of its nucleus. This is why fluorine has very high electronegativity, because it is so small. Now, let's have a look at one last question. Pause the video if you like. Try this on your own. Check for understanding of the properties listed below. Which one is most important in determining the electronegativity of an atom? So let's have a look. A, the number of neutrons in the nucleus. This would not be a determining factor. The number of neutrons in the nucleus have nothing to do with the effective nuclear charge. The effective nuclear charge, remember ZF, has to do with the atomic number. Atomic number is the same as the proton number. We care about the proton number. We do not care about the neutron number, so this is wrong. Next, B, the size of the atom with which it is sharing an electron. That could be true. If we have an atom this large, and we have another atom this large, yeah, definitely the electronegativity would be a very big determining factor, depending how small this one is. But it's also asking about the size of the atom with which it is sharing an electron with. If this size of the atom here is extremely large, then it would work out. However, what if it was like that? They're approximately the same size. So as you can see, it's kind of a conflicting factor. There's a confounding factor with the size of the atom. So it cannot be this one. C, the number of electrons in its valence shell. This one would be wrong as well. It does not matter how many electrons are on the valence shell. If there are more electrons on the valence shell, that just means that the proton count within the nucleus will also be larger as well. If it's larger as well, then they should have the same count. If there were 10 protons, there would be 10 electrons. So it's not as if the more number of electrons would make really a difference, because the proton number count should follow suit on the periodic table. As the periodic table goes down the group or to the right, there should be an increase in atomic number, which would increase the proton number, but also increase the electron number. So it's not too much about the electrons. D, its atomic number. Again, if I were to draw your little periodic table here, and as you can see, if you have an atomic number increasing going downwards, and the atomic number also increases towards the left, if its atomic number is, let's say here, has a high atomic number, but another element here, this is even higher. So this is higher atomic number. This one here is a smaller atomic number. This here, even though it has a higher atomic number, as you can see, its radius is going to be small. It's going to be a smaller size. Smaller atomic radii. This one here, it has a smaller atomic number, but it has a larger atomic radii. The biggest determining factor for the electronegativity has to be the differences of its size. So, if the neighboring atom is really, really big, and the small one is really, really small, the nucleus in here has a strong ability to bring those electrons that are residing over here closer towards it. Has to deal with the size, because the difference between this and this will give you a larger EN. We call this the change, right? The difference. So if this one was, let's say, I don't know, a 1, and this one was, let's say, like a 4.0, the electronegative difference would be a 3.0. It would be a large difference. But as we can see here on the bottom right, the higher the atomic number, smaller the atomic radii. But here, this is a larger atomic radii, despite having a smaller atomic number. So the atomic number doesn't really have to deal with it. It's more so the atomic radii. So this here would be the answer. The atomic radii, regardless where it is on the periodic table. Because on the periodic table, the atomic radii can follow a certain trend. However, it may not follow the same trend as the atomic number. Just because it has a atomic number, a bigger atomic number, doesn't mean it's going to have a larger atomic radii. Or just because it has a smaller atomic number doesn't mean it's going to have a smaller atomic radii. There are trends within the group to follow, but there's also shielding effect as well, effective nuclear charge. Go back to the previous videos that I've posted for the atomic radii. There are determining factors that we have to outweigh the options to. Once you weigh out those options and determine which one has a smaller atomic radii, that's going to be the one that has a very, very strong pull on its neighboring electrons, right over here. So let's say this is fluorine. I know this is not the electronegativity for it, but let's say this is fluorine over here. It has a very, very strong pull with its neighboring electrons beside it that really, really want to go towards the positively charged nucleus. So the answer would be E.